All right. So let's check we're in the right screen. Yes. Okay. So actually, I now realize that there is really the voice. If I search to expert, no, I don't know. It doesn't matter. Auto. Um. Okay. Now I can config. I can configure this here, so I can actually get it to speed faster. That's cool. Hello.
Hey there, what can I do for you?
Oh no, too fast. Talk like a normal person. Hello?
Hi there. How can I assist you today?
Oh, custom. Let's try custom. You're okay. So you're um. Can I just like you are a mathematician expert.
What
Um,
kind
but
of math do you need
also
help
a
with?
great educator like
That.
Richard
Oh,
Feynman.
oh,
Safe. Hello. How are you?
five hellos? Well, I'm doing great, thanks. How about you?
Cool. Look, I'm actually eager to explore. I'm trying to understand what group what blocks of a group algebra are, and I'm like from a very I want to start from a very high level, and see if we can just talk our way through getting into, in detail enough that we can then jump into like some more formal discussion.
Sounds like a fun challenge. Let's start high up. Group algebras are basically a way to mix groups and linear algebra. Imagine you have a group, like a collection of symmetries or operations you can do, say, rotations of a triangle. Now, instead of just doing those operations one by one, you want to do math with them, like adding or scaling them. A group algebra takes all the group's elements, turns them into a basis for a vector space, and lets you combine them with numbers, usually from a field like the real numbers or complex numbers. So, you're building this big playground where group elements act like vectors, and you can add or multiply them in cool ways. Now, blocks are like splitting this playground into smaller, self contained zones. Each block is a chunk of the group algebra that behaves nicely on its own, almost like a mini algebra. They show up when you look at the algebra's structure, especially for finite groups over fields like the
Okay,
complex
let's stop. Let's
numbers.
stop. Let's stop there for a second. So let's peel that off a little bit. So the thing, what I'm struggling with is the notion of um, splitting it into areas or splitting it into sections that kind of behave nicely somehow. I mean, to me, it's like you have the group, and the group has. So for some reason, I have the feeling that if you already think of the group as something you're turning into a basis, that then this is already like a kind of splitting. But forget that for a second. The Give me a second, okay? Don't interrupt me. So if I have an algebra like a group, and I apply this group over a field to construct a field algebra, I understand the concept of basically adding addition and multiplication to the group operation. But then the splitting itself, it's like how what do you mean that the group then behaves in a way self-contained? Can you explain that a bit more?
Sure, let's dig into that splitting idea. When you turn a group into a group algebra over a field, you're giving it a structure where group elements are basis vectors, and you can add them or scale them with numbers from the field, like complex numbers. The group algebra is one big object, but it's not always one happy, uniform thing. It's like a big house with rooms that don't always talk to each other. Blocks are those rooms. They're smaller pieces of the group algebra that act like their own little algebras,
Okay,
and
wait,
they don't.
wait. So let me stop you there. When you say that act like individual small algebras, what do you mean exactly?
They're like mini versions of the whole group algebra, where the rules of addition and multiplication still hold, but only within that block. Each block is a chunk that doesn't get tangled up with the other blocks. It has its own set of basis elements from the group algebra.
Okay,
And when
wait,
you
wait. Do you mean for example that once you're in that, like if you're inside that block, you're always operating within that block, you stay within that block? Is that what you mean?
Exactly. Once you're in a block, All your operations, addition, multiplication, whatever, stay inside that block. It's like a little bubble where the group algebra's rules apply,
So
but it
this
doesn't
means
leak.
so this means that it's impossible by basically operating within elements of that subspace of the field. You can't get out of there, right?
Right, you can't jump out. If you're working with elements just from that block,
Now I get it.
all you
Now I get it. Cool. Thank you. Thanks. That's I've you have to ask the right questions. That makes a lot of sense. Thank you. What about okay, how do we like is there a way to systematically split a group algebra into these, or do you, because I recall from some of the previous conversations where essentially if you like I don't
glad it
know,
clicked.
yeah. Go ahead.
Algebra into blocks, you use something called the decomposition based on its representations. For finite groups over fields, like the complex numbers, you look at the irreducible representations. Think of these as the simplest ways the group can act on vector spaces. Each block corresponds to one of these irreducible representations, or a group of equivalent ones. The process involves the algebra's center, elements that commute with everything, and idempotents, which are special elements that act like projectors onto these blocks. In practice, for a group like S3, the symmetric group on 3 elements, you'd find its representations, and each block would be a matrix algebra tied to one of those representations, keeping things neatly separated. Want to go deeper into how we compute those idempotents, or stick with examples for now?
I would let's try to like. Could you help me build a? Could you help me build a very small example, even using SymPy here in the chat? Like you don't have to read the code out loud, but maybe just write down the code blocks. Can you do that?
Absolutely. Let's build a tiny example using the symmetric group S3, which has 6 elements, 3 possible orderings of 3 things, like permutations. We'll create its group algebra over the complex numbers and show how it splits into blocks. I'll use SymPy to keep it concrete, and I'll explain what's happening step by step without reading the code aloud. Let's dive in. First, S3 has elements, identity, E, 2 cycles like 1, 2, and 3 cycles like 1, 2, 3. The group algebra C treats these as basis vectors. We'll compute the center of the algebra and find idempotents to identify the blocks. S3 has 3 irreducible representations, trivial, 1D.
Can we pause
sine.
for a second? Okay, so let's step back for a second. So you're saying, because I'm curious about the idempotence concept, because essentially the idempotent concept, like, can we explore that a bit more? So an idempotent concept is basically like, are these elements that kind of when operated with themselves go back to some kind of identity or something like this? Like, are these elements that actually have that that enclosing behavior, that that they don't spit another element out of the operation, but actually either themselves or something like that?
Great question. Idempotents are exactly what you're picturing, elements that, when you multiply them by themselves, give you back the same element. In a group algebra, an idempotent, E, satisfies E dot E is E. It's not quite the identity of the group, but it acts like a projector onto a piece of the algebra, like shining a spotlight on one block. These idempotents are key to splitting the group algebra because they mark out those self-contained blocks we talked about.
Okay, so can you say that if you find all the idempotents, then you already know how many blocks you're going to have?
Yeah, pretty much.
Okay.
The number of blocks corresponds to the number of primitive idempotents you find in the center of the group algebra. Each primitive idempotent projects onto one block, and since they're orthogonal, meaning their products with each other are 0, they carve up the algebra cleanly. For a finite group like S3 over the complex numbers, the number of blocks equals the number
Wow, this is so crazy. This is actually very nice because it's very nice because like when you're saying that they are orthogonal, right? Essentially what you're saying is that essentially, yeah, the product is 0. And by 0, do you mean the identity? Because essentially what that means is that these elements combine with any of the other elements. Somehow
No.
it's like I'm like building a picture. It might be wrong, but it's like, yeah, you're kind of like they're orthogonal to the other elements, and so this means that they can't. jump
Yeah,
off to the other spaces?
I think you're asking about how these blocks or idempotents interact with other parts of the algebra. When I say orthogonal, it means that if you take two different idempotents, say E1 and E2, from the center of the group algebra, their product is 0, the actual 0 element, not the group's identity. So E1 dot E2 is 0. This keeps the blocks separate, like different rooms with no doors between them. Each idempotent projects onto one block, and because they're orthogonal, the blocks don't overlap or mix.
When you say they project, what do you mean exactly? I mean, I'm familiar with projections from a geometric sense, but is it because every element, like let's say you have an idempotent, right? You found an idempotent. So how do you, like, if you multiply any other given element of your algebra with this idempotent, does the result tell you something characteristic about that block?
Exactly. You're thinking along the right lines. When I say an idempotent projects, I mean it acts like a filter or a spotlight, picking out just the piece of the group algebra that belongs to a specific block. If you take any element in the group algebra and multiply it by an idempotent E, the result is an element that lies entirely in the block associated with E. It's like projecting a vector onto a subspace in geometry. Only the components in that subspace survive. Here's how it works. Since E dot E is E, the idempotent is like a gatekeeper for its block. If you multiply some element x in the group algebra by E, you get x dot E, which is now in the block tied to E. This result tells you the piece of x that lives in that block. If x had orthogonal nature of the idempotents, leaving only the part in E's block. So, it's a way to decompose the whole group algebra into these isolated pieces.
Yeah, wait. Because we're actually talking about vector spaces, right? That's why this makes a lot of sense. That it's just so nicely from a geometrical perspective, because we're talking about vector spaces, which essentially, in my head, because I can't just go beyond 2 dimensions, but in my head, it's like you're gonna have, so yeah, you're gonna have basically, it's almost like, is it true if I say that, like, let's say in an algebra where we're just talking about like,
Yeah.
no, wait a second, the regular the regular 2D space algebra over the reals, for example, what would be the blocks in that case? Does this question make sense at all?
Yeah, it totally makes sense, and it's a great way to think about it. Let's take a 2D vector space over the reals, which I'll assume you're thinking of as something like array loop, and maybe you're wondering how a group algebra might come into play, or what blocks would mean here. Since you mentioned space algebra, and we've been talking about group algebra, I'll interpret this as you asking about the group algebra of a simple group acting on array loop, or maybe a matrix algebra like M2 array loop, which is the algebra of 2x2 matrices over the reals, because that's a natural fit. If I'm off, let me know. Let's try the group algebra of a small group acting on array loop, say the cyclic group C2, which has 2 elements, the identity and a single flip, like a 180-degree rotation. The group algebra array loop is a vector space where the group elements are basis vectors, so it's 2-dimensional over the reals, with basis E, F, G, where E is the identity and G is the flip, satisfying G2 is E. Now, blocks are about decomposing this algebra into minimal pieces that don't mix. For array loop, we look at its representations over the reals. C2 has 2 irreducible representations over array loop. The trivial one, where both E and G act as +1, and the sign representation, where E acts as +1 and G as -1. Each of these corresponds to a block. Here's the idea, without diving into heavy math. The group algebra array loop can be split into 2 one-dimensional blocks, each tied to one of these representations. The idempotents in the center of the algebra are the key. For C2, the center has basis elements like E plus G.
Okay, stop.
And
It's at this point, I think it's a little too. I got lost. Wait a second. So it's fine. Let's go back. How do you find? So what is the meaning of? Let's. I see that you're using representations of the field over the group, or did you call it like that? Like, to find the idempotence?
No worries. Let's back up and simply, to find the idempotence that split a group algebra into blocks, you don't exactly use representations of the field over the group, but rather the group's representations over the field.
Okay.
Let me break it down clearly. A group algebra, like array loop for a group G over the complex numbers, has a structure that's tied to the group's irreducible representations, ways the group acts on vector spaces that can't be broken down further. These representations tell you how many blocks you'll get and help find the idempotence.
Yeah, okay. Okay. So if you find the reducible representations of the group G over a field F, you actually already have the number of blocks.
Right, you've got it.
Okay.
If you find the irreducible representations of the group G over the field F, say the complex numbers, the number of those irreducible representations tells you exactly how many blocks the group algebra F will split to.
Now,
each irreducible representation corresponds to one block, and the central idempotence act like...
Hello. Can we dive into the definition of a group representation, a representation of a group over a field, please?
Sure, let's dive in. A representation of a group G over a field F, like the complex numbers, is a way to represent the group's elements as linear transformations. Think matrices on a vector space over F, while respecting the group's structure. Formally, it's a function rho G to TLV, where V is a vector space over F, and TLV is the group of invertible linear maps from V to itself. The key is that this function preserves the group operation. For any G, H in G, arrow G dot H, rho G, sir, rho H, where sir is composition of linear maps. So,
it would be great if you could write these things down in the chat while we're speaking, but I think you can't do that, because when you read formulas out loud, I get lost. So, but this is just me. So if whenever you talk about a formula, I prefer if you just put it in the chat in text form. I don't know if you can do that. Is that possible?
No problem at all. I can definitely write formulas in code in text form in the chat while we talk, so you can see them without me reading them aloud. That way, you can follow along visually and not get lost. I'll keep the explanations conversational and pop any formulas or math right here in the text for clarity.
Okay, so go ahead. So can you write down the formula for finding the irreducible, well, what you were talking about, the representations of a group G over F?
Here's the basic idea for a representation of a group G over a field F. I'll write the definition in text so you can see it clearly. A representation of a group G on a vector space V over a field F is a function rho G of V, where TLV is the group of all invertible linear transformations from V to itself, like invertible matrices if V is finite dimensional. The function rho must satisfy. Here, G of H is the group operation in G, and sir means
stop. It's not working. Anyway, because I don't see the formulas here. Maybe it's a bug. But anyway, let's okay. So please, let's stop for a second and do a bit of a reset. Confirm that you're okay with these.
Got it. No problem. I'm totally fine with resetting and pausing for a second. Let's take a breath and figure out the best way forward.
Yes.
Maybe the formulas didn't show up.
Don't worry. What I want to do to explain again is what's the concept of a representation of a group G over a field F. And what you're saying is, if I understand you well, that is basically a representation of the group G is basically I don't know what is it that you're trying to map there. Like, what's the definition of a representation? Like, keep it as simple as possible. Don't bring up formulas. Okay, try to stay at an intuition level. Like, if I have a group G, I know what a group G is. I know what a field F is. And now I want to understand what is a representation of a group G over a field F.
Got it. Let's keep it super simple and intuitive. Imagine you have a group G, like a set of actions or transformations you can do, say, rotating a triangle or flipping a coin. A representation of G over a field F, like the real or complex numbers, is a way to turn those group actions into math you can do with vectors and matrices while keeping the group's rules intact. Think of it like giving each group element a job as a matrix that moves vectors around in a vector space over F. The key is that these matrices play nicely with the group's structure. If you combine two group elements, like doing one rotation then another, their matrices combine the same way, like multiplying matrices. So, a representation is just a way to translate group actions into linear algebra language, letting you study the group using tools like vectors and matrices over the field F. Does that paint a clearer picture?
A
Or
little
want
bit,
me
a
to
little bit. So what you're saying is you take a group, and what do you do? What is like, how do you construct one representation? So do you map the elements of a group to something and then you do something with the group algebra that results out of combining the field and the group, or what do you what's the step to build one of these representations?
Awesome. Let's walk through building a representation step by step, keeping it intuitive. Start with your group G. Say it's the group of rotations of a triangle called C3 with three elements: do nothing, rotate 120 degrees, rotate 240 degrees. To construct a representation over a field F, like the real numbers, you want to assign each group element a matrix that acts on a vector space, and these matrices must respect the group's multiplication rules. First, pick a vector space over F. Let's choose array loop, the 2D plane, since it's easy to picture. Now, for each group element in C3, assign a 2 by 2 matrix that represents its action as a linear transformation on array loop. For example, the do nothing element, identity, gets the identity matrix, which leaves vectors unchanged. The 120-degree rotation gets a matrix that rotates any vector in array loop by 120 degrees. The 240-degree rotation gets a matrix for a 240-degree rotation. The trick is ensuring that combining group elements, like doing one rotation then another, matches the result of multiplying their matrices. For C3,
So
if you
you're okay, so you're essentially, it's like an interpretation. You're building, so you
yeah,
are building a, you're mapping the elements of G to elements, you're mapping the elements of G to elements of FG, right? To elements of the group algebra. Is that right?
not quite.
No.
In a representation, you're not mapping directly to elements of the group algebra yet. Instead, you're mapping each element of the group G to a matrix or linear transformation in a vector space over the field F, like a set of matrices that act on vectors. These matrices live in the world of linear algebra, specifically in something like tris GLV, the group of invertible linear maps on a vector space V. The group algebra, FG, comes into play later as a way to combine group elements with coefficients from F. But for a representation, you're focused on assigning each group element a matrix that respects the group's structure. For example, in the C3 case, with rotations of a triangle, you map each rotation to a 2 by 2 matrix over array loop, and those matrices multiply the same way the rotations combine. The group algebra might use these representations to build its structure, but the representation itself is just this mapping from group elements to matrices. Want to stick with this, or jump to how the group algebra uses these
But
representations?
is it always matrices? Isn't it like, I would have expected that it's something a bit more abstract, right? Because I mean, essentially you can have whatever field you want. It doesn't have to be a field that is, I mean, it can be anything, right? Um, so what I'm trying to understand is what is it that you're mapping the elements of G to? Because essentially I thought when you're building the field algebra, you're just doing all the linear combinations of the elements of the field and the elements of the group, right? Like representations are in a way, like you're they are related. A representation of a group is always over a certain field, right? Is it always really matrices?
No, you're absolutely right to push back. It's not always matrices, and it can get more abstract, which is a great insight. Let me clear this up and keep it intuitive. A representation of a group G over a field F is a way to map the elements of G to linear transformations on a vector space over F. These linear transformations be represented as matrices if the vector space is finite dimensional,
Yeah.
like array loop 2, which is why I used matrices in the example.
Okay.
It's a concrete way to picture it. But more generally, you're mapping each group element to an invertible linear map in text GLV, where V is a vector space over F, and FGLV is the group of all invertible linear transformations from V to itself. These transformations don't have to be matrices if V is infinite dimensional or abstract, but they still need to preserve the group structure. If at G, H, and G, the map rho gray, gray H, rho H, where rho circ is composition of linear maps. Now, about the group algebra F, you're spot on that it's all about taking linear combinations of group elements with coefficients from F, like A1, G1, A2, G2, where AI in F and GI in G. The group algebra is a different beast from a representation, but they're connected. A representation gives you a way to act the group on a vector space, and the group algebra can be thought of as a machine that encodes all possible representations of G over F. Each
Okay.
representation of G induces a representation of the group algebra, F, where elements of F act as linear combinations of those linear maps. So, to summarize, you map elements of G to invertible linear transformations, not always matrices, but often matrices for finite dimensional spaces, on a vector space over F. The group algebra F is a separate structure where group elements are basis vectors, and representations of G help you understand how F acts on vector spaces. The field F can be anything, like real numbers, complex numbers, or even a finite field, and the representation stays consistent as long as it respects the group's operation.
Actually,
Does that
one
help?
question. I now realize one question. So, aside from these, so when you're building like a group algebra, you need
Yeah.
to give you actually need to give meaning to the group operation, right? In that context, because addition and multiplication from the field are known. Do you need to give meaning to? Oh wait, I think I know what you're meaning. I think the group algebra is not necessarily specifying, for example, what okay, so group algebra is not really specifying what does, for example, an element of the field times an element of the group mean, right? And so a representation is a specific interpretation of these. Is that correct?
Yep, you've nailed it. When you build a group algebra, like F, where F is a field and G is a group, you're creating a vector space where the group elements are basis vectors, and you can add them or scale them by elements of F. The field gives you addition and multiplication for the coefficients, and the group gives you a multiplication rule for the basis elements, i.e., the group operation, like G, gray H, for G, H, and G. But you're right, the group algebra itself doesn't define what it means for an element of F times an element of G to act on something. It just sets up the structure where group elements combine via the group operation and field elements scale things. A representation steps in to give a concrete interpretation. It takes the abstract group elements in G and
Okay.
maps them to linear transformations, like matrices if the vector space is finite dimensional, on a vector space over F. When you extend this to the group
Yeah,
algebra,
I think I get it. I think I get it a little, at least like I'm 90%. I need to think about this a bit more. Thanks. That was actually very helpful. Thank you.
awesome. Glad it clicked about 90%. Take your
See you
time to let
guys
it
later.
sink in. I know this stuff can twist your brain in knots at first.